Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Enrique got his PhD from the University of Madrid, and he's been doing interesting work in extracting information from unstructured text, especially the web. So he's going to tell us today recent work he's been doing in Tokyo.
Thank you. So I'm going to speak today, as he said, on mainly learning relationships from unstructured text. And this is kind of unfinished research. It's the kind of things we are working on right now, so some of the evaluations are still not finished, but I thought it might be interesting to talk about this topic because it's the kind of things we're working on right at this moment. And the outline of the presentation is this. I'll start with a very brief introduction about information extraction, as I suppose most of you already know much about it, and then I'll talk about the particular procedure we are using to learn textual patterns to extract information from text. And I'll talk about 3 experiments that have been performed with this pattern learning procedure. The first one about named entity recognition, and the last 2 ones about relationship extraction, to finish with the conclusions and the future work. So, beginning with the introduction, I suppose you already know that information extraction is a task of extracting structured information from text. It was really pushed forward by the message understanding conferences since the late 80s until the late 90s. And there have been much work on this topic. 2 of the most important tasks in information extraction are named entity recognition, which basically consists of finding instances of some particular entity types in text, such as deciding whether this proper noun is a person, or the other proper noun is probably an organization, a business. And secondly, another task that is very relevant in information extraction is the extraction of relationships, such as whether a particular person works for some company or has left a post in a company to join a different company. We are going to focus on learning patterns for information extraction for both tasks. There are also many works on patterns. Initially, most of them were handcrafted patterns that require a lot of time to build and to port to new domains, but which usually have very high precision. So, for instance, if you have a pattern such as this one, you probably know that the thing that is here is a person. And if you have a pattern such as this one, you probably know that the subject of the verb is a person, this is a post, and the complement of the preposition of is the name of the company. And we are going to focus as well on the use of rote extractors to learn these patterns unsupervisedly from the web. Okay, let's go on with the next section. This is the procedure that we use for learning the patterns. It's a very simple procedure, but it has the advantage that it's very fast, both to learn and to apply. So the idea is that we have many text samples representing particular examples of named entities or relationships, and we look to find which are the common patterns in these textual samples and which are the non-shared portions to obtain generalized ones. So if we have text fragments such as these ones, some capitalized word is a new lecture, or professor something is a respected lecture, we want to be able to automatically obtain a pattern such as this one, taking the common parts and maybe creating disjunctions of words or removing things that are not common to them all. And we're using a similarity metric which is based on the edit distance algorithm, which allows some operations to calculate the distance between these patterns, namely insertion, deletion, and replacement of tokens. We'll see very quickly the procedure because probably most of you already know it. The idea is that this edit distance can be calculated very easily just by filling in a matrix. We put the original pattern in the rows and the new pattern in the columns, and each of the cells will contain the edit distance, the number of operations that we have to do to transform the number of tokens from the first pattern corresponding to the row into the number of tokens from the second pattern corresponding to the column. So this matrix is filled in the following way. The first cell means an edit distance of 0, which is the amount of operation to transform an empty string into an empty string. The first row and the first column means the number of operations to transform an empty string into any number of words, so you have to do the same number of insertions, and to transform any number of words into an empty string, so you just have to do that number of deletions. And finally, to fill in a given cell, we always have the following options. If we know how to transform this string into this string, to add a new word, you just have to use this edit distance plus one insertion. So it would be 2 operations. In the same way, if we know how to transform this string into this string, just by adding a deletion, we can transform this one into the other one. And going through the diagonal, if we know how to transform this into this, and these 2 tokens are the same, we can transform this string into this one without any new operation. And if the 2 tokens were different, we'll have to add a replacement operation. So the matrix is filled very easily in this way, and the final edit distance is the value we have at the bottom right corner of the matrix. So in this particular example, we see that there have been 2 operations, an insertion of the word professor and a replacement of new by respected. Well, while filling in the matrix of edit distances, we can also record at each point the operation that was chosen, the one with the minimum number of operations. So we can record at each point whether to fill in the corresponding cell in this matrix we chose to do an insertion, to do a deletion, to do a replacement, or whether the 2 tokens were the same, were equal. And using this second matrix, by filling in, by walking along the path of the minimum edit distance, we can construct a pattern maintaining the common things of both original patterns. So we start at the last cell in the matrix, and whenever we had 2 tokens that were equal, we just keep the token in the final generalized pattern. Whenever we had a replacement, we just add a disjunction between the 2 original tokens. Then we have 3 equal tokens, and finally, if we have an insertion or a deletion, we can add a wildcard to be able to allow anything at that point. And in this way, we can get a pattern that subsumes the 2 original ones. And this algorithm allows for many possibilities. Particularly, we can vary the weight of the edit distance operation depending on many factors, such as the kind of operation, giving a different weight to insertion, deletion, or replacement. Also to the distance of the things that we want to extract. The patterns will be used to either to extract named entities or to extract relationships. So we may give a higher weight to the words that are near the named entity or near the things that are related, and to give low weights to words that are very far away. And also we can vary the weights depending on the part of speech tags of the terms in the original text. And by varying all these weights, it's possible to have many different results. This is just an example. If we start with patterns, it is a kind of, and it is nice of, depending on the weights that we give to the algorithm, the best generalized pattern, the one with the lowest edit distance, might be if the system chooses to do two deletions and one insertion, we just have a wildcard at that position. If the system chooses to do a replacement for A by nice and a deletion of kind, the pattern obtained will be like this. And if the system chooses to delete the determiner and to replace the other two words, the pattern obtained will be like that. So we can play with all these parameters to obtain very different results. So we're going to see three different applications of this procedure to generalize patterns. The first one is named entity recognition. The second one will be learning taxonomic relationships based on WordNet and also meronymic relationships. And the third one will be learning of non-taxonomic relationships unsupervisedly from the web using a rote extractor approach. Right, concerning the first one, named entity recognition, the idea here is to learn surefire rules to recognize instances of entity types. These surefire rules were first named by Andrei Miheb in his system for the last message understanding conference, which was the one that had the highest rank at the time. And the idea is that we use rules with a very high precision, but probably with a low recall, to do an initial annotation of a corpus. And afterwards, we use a machine learning approach, such as a maximum entropy classifier. So this machine learning approach can take advantage of the result of the rules that are supposed to annotate the corpus accurately. And some examples provided by Miheb are the following. If we have a sequence of one or more capitalized words, the verb is, possibly, optionally, the determiner A, 0 or more adjectives, and the name of a profession, we can be pretty sure that the initial sequence of capitalized words are a person. And equally, if we have shares of something, that will surely be an organization, and if we have the something area, that will surely be a location. What we do here is to use the CovenLL 2003 corpus to learn automatically these patterns using this procedure. In this corpus, we have annotated people, locations, organizations, and miscellaneous entities. And these miscellaneous entities may be many kind of things, such as adjectives referring to countries, such as Spanish, French, Japanese. We may find also titles of books, titles of films. We may have many different kind of entities in this class. The procedure followed is the following. For each kind of entity, we initially select a window of 11 words centered in each of the named entities, because we assume that just 5 words to the left and 5 words to the right will provide enough information to know that the thing in the middle is a named entity. And we never cross sentence boundaries. So a couple of examples that are obtained from the CovenLL training corpus are the following. By Hendrik's former girlfriend, something, comma, who lived with him. So the idea is that if we find this sentence in any text, we can be very sure that this will be a person. And also there may be the case that a person name appears alone in a sentence, so the pattern extracted would be like this. A marker of beginning of sentence, the entity, and the marker of end of sentence, which will probably be a very bad pattern to extract it. And we also extract the list of part of speech tag sequences for all the named entities found in the corpus. So typical tag sequences for people names are either 1 or 2 proper nouns, we may find sometimes a conjunction or a preposition inside someone's name. To generalize the patterns, we take all these patterns that were extracted from the training corpus. We initialized as an empty set, which will be the result. And while we have patterns, we take the two with the smallest edit distance, we remove them from the original set, we generalize the two patterns using the previous algorithm, and we apply the generalized pattern to the training corpus to see what it extracts. And using that corpus, we calculate the precision of the pattern. If it exceeds a given threshold, we add the pattern to the set P, so it can continue generalizing, and otherwise, if the precision of the generalized pattern is below the threshold, we assume that it has been over-generalized, so we take the two original patterns and we put them inside the result set. And to apply the patterns, we take each sentence in the test corpus, we look for the left context and the right context of the patterns, and if they apply, we take the things in between, and we check that the sequence of part of speech tags of those things in between were seen as in some instance of a named entity inside the training corpus. And if they were seen, we annotate the named entity as such. This is an example of an annotation. This is an example of a generalized pattern. The wildcards at the beginning and at the end are always removed because they do not provide any useful information. So a possible pattern obtained is comma, entity, a noun source set, another wildcard, I, we, he, or it, can, did, have, think, or wanted. In this experiment, the weight functions that were used to guide the generalized force that in the case of a replacement, the words have to belong to the same general part of the speech class. Only verbs can be replaced by verbs and only pronouns by pronouns, because otherwise the generalized patterns were not very good quality. So let's suppose that we have this example in the test corpus. Today John Smith announced Mary he wanted a car. So we take the left-hand side part of the pattern and we find it in the text. We take the right-hand side of the pattern and we see that it matches with this part of the text. The verb announce, the wildcard would be Mary, he wanted. So we take the thing in between, which is the candidate to be annotated as an entity, and it consists of two proper nouns, which have been seen as a possible sequence for a person inside the training corpus, so this will be annotated as a person. These are the results using a threshold during the generalization of 0.9. So any pattern after the generalization whose precision was in the training corpus below 0.9 was not included in the result. And these are the results taking all patterns, the patterns that applied at least twice on the training corpus, the patterns that applied at least 3 times on the training corpus, and so on, with the idea that the more times a pattern applies, the more sure we can be that the precision estimated in the training corpus is correct. The confidence interval for that precision will be smaller. And this is the precision and the recall values obtained, which, as you can see, are between 94 and 96%. And the recall, as we prune the set of patterns, the recall drops a little bit, but it's still rather good for surefire rules, considering that it's only a first step inside a complete named entity identification system. And for locations, the results were very similar, with precisions around 93-94%, and recall values between 18 and 20%, using the same threshold. Curiously, this system didn't seem to work so well for organizations, which was surprising for us, and we have the feeling that the kind of context in which we can see organization names is much higher, so the generalization couldn't be done so well as in for context for people. So the precisions obtained have been rather lower, and also the recalls have not been very good. And finally, we already expected that the precision for the miscellaneous entities was also not going to be so good because of the fact that it is a very heterogeneous class containing many kinds of things. So it was very difficult to find overlappings between the different contexts. So these are the final results on the two test sets provided by the Common LLL corpora with the values of precisions and recalls. And these values are slightly higher as the ones I showed below, because we also noticed that a typical error for people was that in the Common LLL, the people's titles were not included in the named entities. If there was a title like Mr. or Doctor, they were annotated as outside the named entities, and most of the patterns included the title. So just by adding the small heuristics of taking the titles away of the people's name, the precisions obtained were like 96, 97 for people with also very good recall values, considering that they are just surefire rules, and for locations as well. But as I said, the system didn't seem to be so good for organizations and miscellaneous entities. This system has also been applied as a first step before a maximum entropy approach, and the maximum entropy system, using features such as the two previous words and the two following words, the suffixes of the current word, the previous word, the following word, and also the result of this system included as a feature for the maximum entropy approach. It improved the final F score from 92% to 94% using this rule. Yes?
So I don't know what
in the Cohen 2003, the final F scores were around 94%. So the final F scores, yes. So it's more or less what I obtained using this system before the maximum entropy approach.
Are we getting to the default time? Can I just wait and ask later, or?
You can ask now, I think.
Okay, so you can imagine other ways of you can imagine just taking a more traditional system with the straight machine learning approach,
Right.
and then using different thresholds, right? You have a maximum entropy approach to get a probability out,
Mm-hmm.
and just look, okay, well, let's take all the ones where the probability is very high.
Right.
So do you experiment with that kind of approach at all, or do you just use the approach?
No, not really. I just used the maximum entropy approach in a single configuration, taking always the highest probability result without any threshold.
You did try, this was the only technique you tried.
Right.
For getting high.
Mm-hmm. That's right. Using this to improve the maximum entropy one.
Right, I guess what I'm saying is that if you want high precision results, you take one of those traditional systems, and you just set the probability very conservative. Like Roman anything else,
Mm-hmm.
the max time, just max time return to probability, so you only take one there, 98% or 7% or,
Mm-hmm.
and that might, and then you only need one system also. You don't need to have these two separate systems. That would seem like a natural
Mm-hmm.
alternative.
Right. Yes.
Okay, anyway,
Okay, so this was all about the name entity recognition, and the next experiment was about learning taxonomic and meronymic relationships. So the idea is very similar as before. We should start with original textual patterns that represent relationships. For instance, patterns such as lithium is the lightest solid element in the periodic table, or Venus is the second planet from the Sun, indicate that lithium is a hyponym of element and Venus is a hyponym of planet. And if we have a pattern such as London is the capital city of the UK, this is representing a meronymy, a part of, really a holonymy relationship, because London is a part of the UK. Here we didn't have any training corpus such as we did for named entities, which annotated semantically with relationships. So what we did was to build this corpus automatically from WordNet and from the Wikipedia. Initially, because we can exploit WordNet to get the existing annotated semantic relationships for hyponymy and for meronymy between the synsets, and we can exploit the Wikipedia to have a textual corpus from which to learn the patterns. So the initial thing that we did, this experiment was done with the simple English Wikipedia because this was a prototype to see how the system worked, and the simple English has the advantages that the size is much smaller, and also the kind of syntactic structures that we're going to find inside the text are also simpler. So the first thing that we did was to associate each Wikipedia entry with a WordNet synset whenever possible. And we used a matching algorithm basically inspired in word overlappings between the definition, the word of the synset in WordNet, and the definition in the Wikipedia. Actually, we used a vector space model approach. We extended these definitions with definitions from hyperonyms and hyponyms, and we also tried to find the genus word in both of the definitions in order to improve the matching. And finally, we obtained about a 90% accuracy in this matching. After the annotation, we took 200 random Wikipedia pages, and manually we examined whether they had been correctly associated to the WordNet synsets, and the final precision for this matching was around 90%. And finally, expectedly, this Wikipedia entry, Jupiter planet, would be associated with the first WordNet synset containing the word Jupiter, the largest planet and the fifth from the sun, but not with the second synset, which is the Roman god. Once we have most of the Wikipedia entries associated to WordNet synsets, we build the training corpus in the following way. We extract all the sentences from the Wikipedia that satisfy the following constraints. The sentence has to be inside an entry and contain the name of the entry, and the subject has to contain a hyperlink to another entry which has been associated to a synset in WordNet having the required relationship. So in the case of hyperonymy, we have here an entry for Jupiter, which was disambiguated to the WordNet synset Jupiter as a planet. And we have a hyperlink. In this sentence, we have the word Jupiter, and we have a hyperlink to the entry about planet. And this entry about planet had been disambiguated as being the same as this synset planet inside WordNet. So in this case, all the constraints are satisfied. We have the entry name. We have a hyperlink to a hyperonym of Jupiter in WordNet. So that sentence is extracted as an example of a hyponymy relationship. The hyperlink will be always replaced by the keyword target and the entry term by the keyword hook. And the final pattern obtained will be hook is the fifth target from the sun, where target is always a hyperonym of hook. These are a few examples for the four relationships considered. For instance, in the entry for sodium, we extracted the sentence, hook is a non-metal target because sodium is a non-metal element. Hyperonymy, in the inverse relationship for hyponymy, in the entry for animal, we had the sentence, we say that these animals are omnivores, and because omnivore is a hyponym of animal inside WordNet, this was extracted as an example of hyperonymy. In the case of holonymy, the part is a part of relationship In the entry for Reykjavik, we found the sentence, Reykjavik is the capital city of Iceland. So this was the pattern extracted. And in the case of meronymy, in the entry for solar system, we found the sentence, planets in our solar system, Mercury, Venus, Earth, Mars, etc. So because solar system is a meronym of contains Venus, this was extracted as an example of meronymy. In this example, you can see a feature that we observed in the text. We didn't know beforehand, but we observed that generally, in the case of hyponymy and holonymy, there is just in the sentence one hyperonym or one meronym. But in the case of the relationships hyperonymy and meronymy, most of the times they are represented in the text with enumerations. If an entry about the hyperonym contains a hyponym, it will probably say things like examples of animals are cats, dogs, will enumerate a list of hyponyms. And in entries about the solar system, we see an enumeration of the constituent parts of the solar system. The generalization is similar as before. We take all the patterns for one relationship in a set. We initialized the resulting set as an empty set, and while we have seed patterns, we take the pair with the smallest edit distance, and we set a threshold to stop if the edit distance of the two most similar patterns exceeded the threshold. Otherwise, we take the two patterns which are most similar, we obtain the generalized pattern by generalizing separately the left-hand side, the middle-hand side, and the right-hand side of the patterns, and we estimate the precision using the whole Wikipedia and using WordNet. We apply the pattern to the Wikipedia, we see the things that are extracted from that pattern, we go to WordNet to see whether there is a relationship between each of the pairs, and in this way we estimate the possible precision of the pattern. So if the estimated precision is below the threshold, we don't generalize the two original patterns, we return them as they are, and otherwise we generalize them and we add them to the set so they can continue generalizing. And these were the results on the simple English Wikipedia. The number of patterns is not so high because of the size of the training corpus. There were about, at the time there were about, I think 4,000 or something like that, between 2,000 and 4,000 entries in the simple English Wikipedia. So we just had a few hundred of patterns initially. In the case of hyperonymy and meronymy, most of the patterns just contain the target, the hook and the target term, and no words around, or they were enumerations which are not properly handled by this procedure, so there were very few generalized patterns. In the case of hyponymy and holonymy, there were around 20 generalized patterns. And this is the number of extracted relationships. The relationships that were already in WordNet were discarded because they were already known, and the new relationships were all evaluated by hand. And the precisions, in this case, we set, in this experiment, we say the threshold to 0 because we wanted to get all possible patterns without, regardless of the precision of the training corpus, and even with a threshold of 0, so we just generalize everything and we don't consider the possible pattern during the possible precision during the training, we obtain results of precisions between 0.61 and 0.69 for the extracted patterns for hyponymy, holonymy, and meronymy, which are more or less the same results that are reported for some handcrafted patterns for these relationships, such as the patterns used by Marty Hirsch in the year 92, which were written by hand, but the precisions obtained are rather similar than this. This is an example of some patterns that were found, the number of times each pattern matched on the Simple English Wikipedia, and the precision as evaluated by hand. This is when extracting new results not seen in WordNet. So we can find patterns such as entry, hook is a type of target, hook is the target in England, things like that. And this is the example for holonymy. Is a part of relationship. And because of the characteristics of the Wikipedia, which is encyclopedic, most of the part of relationships that were there were referring to sublocations. So most of the entries were things like entry is a city or is a province in target, entry the capital city of target, entry was one of the countries, one of the states in target, things like that. Right, so to finish with the third experiment, in this experiment we have tried to learn any kind of relationship, a non-taxonomic relationship from the web, and in this case we don't use any training corpus, so this is the experiment that is really unsupervised compared to the previous ones. We want to find relationships such as author, work, person, birth date, person, birthplace, person, death date, things like this. And rather than having a training corpus, we are going to use a rote extraction approach. And the basic idea of this approach is the following. We have initially a seed list with a few pairs of words that are related. If we want to find patterns to extract birth dates, for instance, we may have a pair in the seed list such as Mozart and the year in which he was born. We perform a search on the internet and using both words in the pair, Mozart and 1756, and we collect a training corpus of documents containing both keywords from the seed list pair. Using this corpus, we extract all the sentences containing both keywords at the same time. So we may obtain patterns such as this one. Hook was born in Target. Or hook, open parenthesis, target, hyphen. Or even if we have a sentence just with Mozart and the birth year, we extract a pattern containing only the hook and the target. Next, it's important to estimate the accuracy of these extracted patterns because some of them may be very accurate, some of them may not be so. So we collect, in previous approaches, the thing done is to collect a development corpus including just the first keyword in the pair, just Mozart. And using this corpus, we apply all the patterns to the corpus and we estimate the precision in the following way. Every time that the pattern extracts Mozart together with the right birth date, we assume that it is a correct result. And every time that the pattern extracts Mozart with a different thing, we assume that that result is wrong. So in this way, the accuracy is estimated and a set of patterns with an accuracy over a threshold is produced. But this procedure that has been reported in several works before has a couple of problems that I describe here. First of all, because of the fact that the accuracy estimation is done using the same elements in the seed list, I believe that the resulting accuracy estimates are probably too high, higher than they should be. Let's suppose that we are collecting patterns for the relationship is located at, and we use a seed such as the Chrysler building in New York. A possible sentence that we may find in a text is New York's Chrysler building. So from this sentence, the pattern targets hook would be extracted. Now, in the way in which the accuracy of this pattern is calculated, we download a development set for Chrysler building And we try to find this pattern in the development set in the cases in which it extracts the Chrysler building. So all the cases in which we have something is Chrysler building. And because this is only evaluated when the hook is something in the seed list, most of the times the thing in the target will be the correct thing. Because if we search on internet for this pattern, having here the Chrysler building, most of the times we're going to have here New York. A few times we may have the name of the architect of that building or a different thing, but most of the times we'll have there New York. So the accuracy for this pattern, the precision estimate will be very high, higher than it should be. And we may have results such as this, indicated by Ravichandran and Hobby in 2002, in which they indicate that for the relationship inventor, the pattern targets hook was obtained a precision estimate of 1, that targets hook a precision estimate of 1, and next for the pattern discovery of targets hook obtained a precision estimate of 0.91, and for the relationship is located at targets hook obtained a precision estimate of 1. In their approach, this is correct because they were next applying this system for a question answering system, and because of the particular application that they had in mind, that they were answering questions, most of the times the question itself is indicating where they're looking for an inventor, for a discoverer, for a location. So in their particular case, that was useful. They were using the relationship extraction in a very particular, with a very particular application in mind. But if we want to use this for general purpose relationship extraction with no application in mind, we just want to annotate the relationships in text, we cannot allow this to happen because the same pattern cannot have a precision of 1 for 2 different relationships. It is an ambiguous pattern that may be used for the relationship inventor, discoverer is located at, author work is a part of, possession, it may be representing many different relationships. And the second problem that we saw in this approach for general purpose relationship extraction is that the way this is estimated is only valid for relationships which are n-to-1. Many people can be born in the same date, but for everyone there is a single birth date. So if we want to use it for relationships such as author work, and we have a seed pair such as Charles Dickens, A Christmas Carol, and in the development set we extract a pair such as Charles Dickens and a different title name, we don't have any information to know whether that different book was also written by Charles Dickens or not. But we should not assume that it is not correct because it's not the one that appeared in the seed list. So in our approach, we use the following information as input. I hope you can read it from the end. We are going to learn patterns for many relationships at the same time. We start with an input table in containing the name of each relationship to be able to annotate it, a file containing a seed list for each one of them, the cardinality of the relationship, n-to-1, 1-to-n, 1-to-1, n-to-n. We also record where the system should be aware that the hook and the target are probably annotated by the named entity recognizer as a person, as a date, or whether it is something that is not processed by the named entity recognizer, so it can be any sequence of words. And finally, we add just 1 or 2 patterns that we are going to use to query the web in the case that we are not sure about whether an extracted pair is correct or not, to improve the estimation of the precision of each pattern. And the approach is the following. We collect, as before, the corpora including both the hook and the target. We extract the sentences from that corpus, and we generalize using the edit distance as before. And now we keep all the intermediate patterns that we obtained during the generalization. We keep all the initial patterns and all the intermediate and final generalized patterns, every one of them. And next, in a second step, we calculate the accuracy, we estimate the accuracy of all of these patterns that we obtained before. So for each relationship, we collect not only a corpus containing a hook for each of the seed pairs, but also another corpus containing the target. And next, again for every relationship and for every pattern, ideally we apply the pattern to all the corpora corresponding to the hook and to the target of every seed pair in every relationship, all of them. Because these corpora are very large and we are using many relationships, we are learning several relationships at the same time, it would be very slow to apply the patterns to all of them. So what we really do is to, for each pattern we select a random subset with files from all of the corpora, and we do the evaluation of this random subset, which is smaller. And next, for every pair extracted by this pattern from this hook corpora and this target corpora, if it appears in the seed list for this relationship, we consider that it's correct. If it appears in the seed list of a different relationship, we consider that it's incorrect. If it appears with a different target and the cardinality has a 1 in the second place, we know that it's incorrect. And if it appears with a different hook and the cardinality has a 1 in the first place, we can also know that it's incorrect. And last of all, if we have any idea whether the extracted pair is correct or not, we query the web using the sample sentences. And we hope that in some cases, if the pair is correct, using the simple queries that I showed before in the table, there will be some web page containing that pattern. So if there is at least one result, we assume that the pair is correct, and otherwise we say that it will be probably incorrect. These are a few examples of patterns found in the web corpora for birth year, hook, and between parentheses the birth year and a number which will be the death year, and end of sentence, or things like a description of the person, who was born on the first of some year, of the first of some month, and the number of the year, and so on. For birthplace, things like who was born in Target. For author book, things like hook, author of, and the title of the book. Odysseus, based on the title of the book and the title of the author, epic, and so on. And for capital country, things like who is the capital of Target. And as you can see, there will be always patterns such as this one, hook, comma, target, which may be referring to the capital country relationship, but which may also be referring to many other kind of relationships. So these should be filtered out by the accuracy estimation step. This is a result of a preliminary evaluation. We used about 20 relationships that you can see here. This is the size of the seed list that we used, the number of patterns that were extracted from the training web corpora, the number of patterns after the generalization step, and finally the number of patterns after estimating the accuracy and filtering those that had an accuracy below 0.5. This is an example, and in this example you can see some patterns obtained for the relationship birth year, subject, and the birth year and a hyphen. They are most of them very similar. We can have a beginning of sentence marker before the subject. We may have a comma or a colon before the subject. The hyphen may be simple or double. Here we have a wildcard, so this may allow for many things here in between. And this is the number of times that each pattern applied in a 1,000 random subset of the development corpora. And you can see here the accuracy of each of these patterns using our estimation procedure. The accuracy that would have been obtained if we have used the estimation procedure based only on the hooks, the one that is used in previous works, and this is the real accuracy of the patterns if we evaluate all the extracted pairs by hand. And you can see that in this case the accuracy estimated is most of the time it's 1. It's very high because this is only applied to the extracted patterns in which the hook appeared in the seed list. If the hook didn't appear in the seed list, the pair is not used in the estimation step. In total, using all patterns, regardless of their precision, there were 436 pairs extracted. Using the previous precision estimate procedure, we would have obtained a 0.81 estimate for all the set of patterns altogether. Using the new procedure, the estimate was 0.46, and the real precision estimated by hand is 0.54. So you can see that this value is much nearer than the real one. Also, this estimate is also a bit conservative because when it doesn't know anything about the pair, what it does is to consult the web, and it's not always guaranteed that we're going to find in the web the sample query that we put in the input table. So there may be cases from time to time in which the extracted pair is right, but we can't find it in the web, and it's supposed to be wrong by the algorithm. And this is also a preliminary result taking all patterns, not filtering them by precision. And we took a sample of 20,000 entries from the English Wikipedia using the dam from 7th of April this year. We applied all the set of patterns from all the relationships to this subset, and the system, every time it finds a possible relationship, it annotates it inside the Wikipedia corpus using the annotation formalism for the Semantic Wikipedia, which is being developed at the University of Chrysler. And this is the results for this preliminary evaluation by evaluating by hand a sample of around 200 pairs for each of the relationships. And you can see that the precision estimates are very varying, but you also have to keep in mind that there was no rule pruning. Although we did the accuracy estimation, we didn't prune the set of rules. So this includes both the good rules and the wrong rules. And you can see that anyway, for things such as birth year and death year, without any pruning, the precision results were very good. So with the pruning, probably we can obtain results usably, even in a commercial system. But for the other relationships, if we don't do the pruning, the results are very varying and still should be improved. So to finish with the conclusions, I have described here some work in progress about learning patterns for information extraction. They have been applied for name entity identification using the co-NLL training and test corpora. The accuracy estimation is done very easily because we have an annotated corpus, and the precisions of the rules are in the range 0.28 to 0.97. In the second experiment, we have learned taxonomic and meronymic relationships. The original resources were warned and the Wikipedia that was disambiguated automatically, and the accuracy estimation is based on the relationships that are already inside WordNet, and the results using the whole set of extracted rules are precisions around 0.6, 0.7. We want to play now with pruning the set of rules using this accuracy estimation to see how this can be improved and how it affects recall. And last of all, the last experiment is about learning binary relationships using a rote extractor approach. The accuracy estimation is based on all the information that we have in the input table for the system, and the results still are varying depending on the kind of relationship. For some of the relationships that are very good, for some of them it still has to be very much improved. And concerning future work, my first interest is about my daughter, Irene, and next we'd like to extend the formalism for the patterns to allow some things that we have not implemented yet, such as allowing to have any word of a given part of representing that we may have any word of a given part of speech tag inside the pattern, or including semantic classes using WordNet inside the patterns. We also the second one was already finished. We also want to, but we want to play as well with different machine learning approaches to see how these patterns affect different machine learning approaches, such as support vector machines, to see if they are still useful as they were for maximum entropy. We want to test as well this system for different languages, because it doesn't have anything that is language specific apart from the part of speech tagger. So we might apply it for name entity identification for Dutch and Spanish, as we have the training and test corpora available. And also we can use it for finding binary relationships in other languages. We can use the Euro WordNet and the Wikipedia in Spanish and Dutch and Italian to see if the results are similar to those obtained for English. And we are also working right now in applying the system for the rote extractor to annotate the Wikipedia in a larger scale. We are annotating the whole Wikipedia with about 100 relationships. And still, we also want to rerun the experiment that we did with about hyponymy and meronymy on the simple English Wikipedia. We want to rerun it on the whole English Wikipedia to see whether it learns more varied patterns. And last of all, concerning the example that we saw before about the genitive construction, hooks, pattern, that it's very ambiguous, because it may refer to many relationships at the same time. Even though it is very ambiguous, if we first apply the patterns for hyponymy, we believe that information would be very useful to disambiguate these kind of patterns, such as the genitive construction. Because if we have applied the patterns for hyponymy and we have discovered that in a given Wikipedia entry it is talking about a writer, we have enough information to know that this pattern probably is referring to the relationship author's book. And we know if we know beforehand that the hook is an architect, that pattern probably will be referring to the relationship architect building, and so on. So we want to take into account the results of the hyponymy patterns in order to improve the precision of the patterns for non-taxonomic relationships. And finally, just to say that this is not all the kind of things that I do, because I have also worked on other topics, such as classifying terms inside ontologies using distributional-based approaches, text summarization, e-learning, such as automatic evaluation of students' free text answers. And I have my own computational linguistic toolkits for English and for Spanish. So anything that you may want to ask to me about this presentation or about my previous research, I'll be very happy to answer you. This is all. Thank you very much.
Have any questions? Also, if you'd like to talk to the speaker.
So, did you try other ways of, you showed us the algorithm that used for putting the patterns together. Could you look at any other ways of putting patterns together, or think of that as similar to producing a Markov model? Did you look at anything else in that space, or just that?
We just focus on this algorithm. We played, as I say, by changing the weight function for each of the operations, depending on several parameters, but just working on this algorithm all the time. Because we believe that still there are many things that can be tested inside this framework.
Thank you.
Thank you.
And the speaker.